So we're starting chapter 5 today, and chapter 5 is really the last chemistry intensive chapter that we're going to get into this entire semester. Chapters 4 and 5 are really the last big chemistry kinds of chapters. After chapter 4 and 5, we're getting more or less into applications of chemistry. So using these chemical concepts to construct our understanding of why certain materials are corrosive or why certain materials are oxidizers, why they behave the way that they do, why this particular chemical over here is dangerous and this one over here is not. So once we get through this chapter, two things we'll start to notice. One, we'll go through a lot of the units a lot more quickly because there isn't going to be as much background to cover. And two, it's going to get a lot more specific knowledge. It's going to kind of fall into this. So we're going to start with just kind of the basic concept. The basic concept of chemistry surrounds the chemical reaction. The chemical reaction is given to us and shown through a chemical equation. Chemical equations are essentially the basic language of chemistry. They tell us what happened, what we started with, and what we're ending with. And they are constructed in this way. The things that we start the chemical reaction with, from now on, we will refer to those as reactants. Those are written to the left side of an arrow in the chemical reaction. The chemical formulas for the substances that ultimately form, the stuff that we end a chemical reaction with. Things that we will refer to from now on as products. These are written on the other side of the arrow. And so the basic construction of a chemical equation is like this. We have our reactants on the one side of the arrow, and they are going to the products on the other side of the arrow. Now, in the previous chapter, we got a lot more detail about what chemical formulas were in terms of, why do what the little numbers mean, why do we arrange them the way that we do, the difference between a ionic compound that's made out of metals and nonmetals versus molecular compounds that are made out of just nonmetal elements. And now we're going to see those different kinds of compounds finding their way to each other and reacting in some kind of interesting way to give us different kinds of reactions, different kinds of products. And as we go through the rest of this chapter into the second half of the semester, that's when we're going to get into the kinds of reactions that ultimately lead to things that are not as good as they need to be, or things that are potentially dangerous. Now, a chemical reaction is capable of giving us as much or as little detail as we want. One of the details that can be given to us are the physical forms that each of the reactants and products are currently in when the reaction takes place. Those physical states of matter are indicated by these letters, S, L, G, and A, Q. S, of course, standing for a material in the solid phase. L, standing for a material in the liquid phase. G, standing for a material in the gas phase. And AQ, standing for a material in the aqueous phase. Now, thus far, we've talked about solids, we've talked about liquids, we've talked about gases. We have a good idea what each of those are. Anyone give me an idea what we might mean by aqueous. Okay, seeing a lot of no's, a lot of shaking our heads. No. That's a supercritical fluid. That's not too many reactions occur with supercritical fluid because the temperature and pressure are just so high. No. Let's break down the word aqueous, aqueous, aqua, water. Okay. Now, aqueous doesn't mean that the substance is water. Clear? Okay, it means it's dissolved in water. So most of the solution or most of the reactions that we do involve materials that have been dissolved in water and are reacting in that dissolved state. And this is kind of an important one because, again, most of the stuff here on planet Earth is water. You know, our bodies are mostly made out of water. The majority of the surface of the Earth is water, and lots of chemical reactions take place in the water. Lots of things dissolve in water. And so the aqueous phase is not one that is something that we take lightly. It's actually quite important. And a lot of the reactions that we do are composed and done in aqueous phases, whether we realize it or not. Now, most of the reactions we've talked about to this point haven't really dealt with too much of the aqueous. We've been talking mostly about things like combustion reactions. But if you think about some certain kinds of things, most of the stuff that we encounter that we think of as acid or we think of as base are actually solutions. I go to clean the toilet in my home. I use something like Snowball or another one of those non-bleach toilet bowl cleaners. Well, even if I use the bleach, none of that stuff is actually the pure chemical that I'm putting on there. It's a solution. It's that chemical dissolved in water that I'm putting onto the surface to help clean it. Now, various versions are going to be more concentrated than others. But depending upon the nature of the substance, so Snowball, for example, is actually hydrochloric acid, which is, the works is also hydrochloric acid, which is why, if you're familiar at all with the works bomb, that's why it works. The reaction that takes place is the aluminum replaces the hydrogen inside of the solution. And so the hydrogen becomes free and starts to fill up the container with hydrogen gas. And eventually the pressure inside becomes too much. And that's basically how most bombs work. The pressure inside of the vessel becomes too much for the container explodes as a result. So we're going to talk a good bit here about these kinds of chemical reactions. And when it comes to chemical reactions fall into really 5 main primary states. 5 different ways of characterizing chemical reactions based upon common ways of working. And the 5 different ways are synthesis reactions, decomposition reactions, replacement reactions, and replacement reactions we can break down into 2 subcategories, the single replacement and the double replacement. And then finally, combustion reactions. Each one of these 5 types of reactions has hallmark signs, telltale markers that let us know that this type of reaction is taking place. And by helping us to identify which kind of reaction we are looking at, it actually does a lot for us in terms of helping us to figure out what the primary dangers are. And from a chemical standpoint, actually makes it a lot easier to balance it because we kind of know what we're looking at and what kind of tricks we can apply based on the situation. So let's look at each one of these in turn. So we'll start with the synthesis reaction. Synthesis reactions, also known as combination reactions, are given by this telltale sign. We have a single product being formed out of multiple reactants. That's what let us know that we're dealing with a synthesis reaction. Synthesis literally means bringing together. And here we are bringing together multiple reactants and coming out with one product. Now, on each of these 5 slides, I'm going to give you a general formula. That general formula is going to give us a means of kind of showing overall what the reaction looks like. But understand that in these cases, X and Y are not actual chemicals. They're standing in for chemicals. And the chemicals that they're standing in for could be elements or compounds. They don't have to be one, they aren't tied to one or the other. So for example, hydrogen gas, an element, reacting with chlorine gas, another element, will give me hydrochloric acid, HCl. And in reality, if I just have the gases, if I don't have water vapor present at all, what it will give me is hydrogen chloride gas, which in itself is not acidic, though it is nasty. But as soon as it comes into contact with any kind of moisture-based surface, instantaneously acts as an acid. So if there were HCl gas in this room right now, we probably wouldn't know it until it started to be absorbed by our skin or in our nasal passages, and then it would start burning like crazy. Because HCl itself doesn't have too much of an odor. It's got a little bit of one. But its acidic effects aren't really realized until it actually dissolves in water. Another example, sulfur trioxide gas. Sulfur trioxide gas can react with water to make sulfuric acid. This is more or less the basis, or one of the bases at least, for the formation of acid rain. Acid rain comes into 2 different forms. There are the nitrogen-based acid rain products. Those come mainly from pollution, from things like incomplete combustion of fossil fuels, smog, those kinds of things. Sulfur-based ones can't come mainly from more on the accident side, things like burning tires, or other kinds of sulfur-based products. Tires and rubber are probably the most common. And when those gases make their way up into the atmosphere and they interact with the water vapor up in the atmosphere, they become part of the clouds. And that formed acid is what ultimately falls down. That's what gives us acid rain. That's why if you take the pH of rainwater, it can come in anywhere in the range of 5 to 6.5, so slightly on the acidic side. And the reason for that is those pollutants picking up little bits of acid along the way, and they kind of come regardless of where you are. Decomposition reactions. Decomposition reactions are essentially the opposite of synthesis reactions. Synthesis reactions, we had two or more reactants coming together to make one product. In a decomposition reaction, we have one product, or excuse me, one reactant, and it breaks apart into multiple products. These kinds of reactions usually require heat, light, or electricity to actually occur. Very few of these reactions actually happen on their own. Breaking bonds always requires energy. And for a decomposition reaction, that is essentially what you have to do. You've got this one uniform reactant, and you've got to break its bonds apart to get it to separate. That is going to require energy of some sort or form. Now, depending upon the nature of the chemical bonds, one of those three things will be enough to do. Some of them, it just requires a little bit of heating. Put it up to a hot plate, a Bunsen burner, you name it. It'll start to break apart, decompose, and go on its way. Some things like hydrogen peroxide are light sensitive. If you ever notice, hydrogen peroxide is always sold in brown bottles. The primary reason for those brown bottles is because the decomposition of hydrogen peroxide is light induced. The brown bottle helps block out some of the light to help keep the hydrogen peroxide shelf stable for a longer period of time. Electricity is kind of used in the more extreme cases. Water. Water is a real good example of this. The bonds that make up water are really strong. But hit it with a good dose of electricity, and that is enough to break those bonds between the hydrogens and oxygens and get pure hydrogen to form on one side and pure oxygen to form on the other. That particular process you know better as electrolysis. And there are other kinds of electrolysis reactions out there. Not all of them are decomposition reactions. Basically, any reaction that requires electricity to happen falls under that name. So under examples, already mentioned this one. This one requires electricity to split the water. Magnesium carbonate. This is one where you can basically just heat it. And if you heat it up, you'll get magnesium oxide and you'll get carbon dioxide as a result. This one's a little bit tougher to see. If you see it demonstrated in a lab, usually what they will do to show that the carbon dioxide is formed is they'll do a flaming splint test, where as you're heating it, the thing you have to recognize, magnesium carbonate is a white powder. Magnesium oxide is also a white powder. The only way that you can really tell that carbon dioxide is formed is that you can either see the gas, which is kind of hard, or you take advantage of the fact that you know that carbon dioxide is used in fire extinguishers and is a really good source of blocking oxygen from a fire. And what you do is you take a piece of wood that's on fire, you put it down into the vessel, and you show that the vessel basically snuffs out the fire. Then you pull out the splint again, it bursts back into flame, and you can do it over and over a couple of times. So that's decomposition. Replacement reactions are a little bit more difficult. Replacement reactions happen when one element replaces another element inside of a compound. That is the general definition of a replacement reaction. Now, like I said, replacement reactions come in two forms. There's the single replacement reaction, and then there is the double replacement reaction. Now, the difference between the two is all about how many compounds are present in the reaction itself. A single replacement reaction has a single compound on each side of the reaction. That's what makes it single replacement. And you can probably guess that the double replacement reaction has two compounds on each side. That's why it's called double replacement. Now, the thing that is interesting and worth noting here, the elements that replace each other have to be similar in property. What I mean by that is the things that have positive charges are going to replace other things that have positive charges. Now, I usually like to generalize that and say that metals replace metals and non-metals replace non-metals. Where that gets tricky is the bit with hydrogen. Hydrogen is a non-metal, but metals will replace hydrogen. Again, think about that Works bomb that I was talking about. You're replacing aluminum with hydrogen. The hydrogen is in the acid inside of the toilet bowl cleaner. So you've got the hydrogen dissolved in the acid. You've got the aluminum metal sticking in there. The aluminum goes into solution and replaces the hydrogen. The hydrogen comes out of the solution and starts to fill up the container with gas. That's ultimately what happens. That's ultimately why it works. That's the replacement part. So in these reactions, we are going to have something that is a metal, or excuse me, something that is an element outside of solution that is going to replace another metal that is inside solution. So magnesium replacing the nickel. As a result, the magnesium becomes dissolved in the water, and the nickel comes out of the water. Iron replaces the copper. The iron goes into the solution, the copper comes out of the solution. And so this is where those phase designations really can help us to see what's going on here. Because if we look at it from that standpoint, then what we can see we've got a solid here, aqueous here, aqueous here, solid here. We've got solid here. Aqueous here. Aqueous here. Solid here. So we can see the magnesium went from being solid to aqueous. The nickel went from being aqueous to solid. We went from inside the solution to outside the solution. That's the replacement part. The nitrates, they didn't do anything. They were aqueous before, they're aqueous after. Basically, what we see in a lot of replacement reactions are karyons. Ions, molecules that don't do anything. They just kind of stay where they are, and they more or less don't participate in the reaction. They're just there because we need something to balance the charge. Right, double replacement. Double replacement reactions, two compounds on each side. And again, we're seeing switching over occurring. The difference here is that for the most part, all the stuff that we're looking at at least initially, is aqueous. Silver nitrate and the sodium chloride, both in solution. Sodium nitrate in solution. But you can see, if we look at it from the standpoint of switching, even though a lot of the stuff is still in solution, we're switching partners. The silver was with the nitrate, now it's with the chloride. The sodium was with the chloride, now it's with the nitrate. From an observational standpoint, there are some key marks for double replacement reactions that usually let us know that something has occurred. One of those is something called a precipitate. I put the two solutions together, I get a solid product forming out of those two solutions. We call that a precipitate. The second is the formation of a gas. Have you ever done the volcano experiment when you were in elementary school or middle school, or any other baking soda and vinegar derivative? That is an aqueous reaction, that is double replacement. The acid in the vinegar is reacting with the bicarbonate ion in the baking soda to create carbon dioxide gas, and the carbon dioxide gas gets trapped, and eventually, you get trapped up enough, you get enough reaction occurring quickly enough. That becomes the basis for that volcano reaction that you're seeing. So formation of a gas is another marker. The last one, evolution of heat. Sometimes you'll see multiples of these. So the sodium, the baking soda and vinegar reaction, if you hold on to that bottle while that reaction is occurring, it does get warm. The reaction is releasing heat as it does. And such is the case for a lot of acid-base reactions, because most acid-base reactions fall into this category of double replacement. Now, reactions like this bottom one, if you look at it on its surface, it doesn't seem all that special. I have sodium fluoride, which is aqueous, toxic, but aqueous. I have hydrochloric acid, which is corrosive and aqueous. I have sodium chloride, which is aqueous, but pretty benign. I've got hydrochloric acid, which is also aqueous. So you may look at this and say, okay, I see that they've switched places. What really is going on here? What's so different? Well, here's the real difference. This hydrofluoric acid is nasty stuff. I mean, nasty stuff. Hydrofluoric acid is something that if it gets airborne, you do not want to be around it. The fluoride ions will actually start to react with the calcium in your body and start to basically degrade you from the inside out. And hydrofluoric acid is something that, because of its reactivity, mainly driven by the fluorine ion in it and the reactivity of the fluorine itself, you've got to be real careful about how you store it. It eats away at silicates, it eats away at borates, which means you can't store it in glass of any kind. It'll eat through it. You gotta store it in some kind of polymer, usually some kind of Nalgene or some other kind of plastic variant. And you gotta keep it under tight seal because again, that seal gets broken and the hydrofluoric acid in the gas form gets out, it can really do some damage to people. So nasty stuff, that one. All right, and this is where we will stop for today. Didn't get all the way through it. Still wanted to talk about combustion. Combustion is actually going to be kind of an easy one to talk about when we pick it up on Monday, or not on Monday, on Friday, because it's a lot of reactions that we've seen before, and they all fall into a very set pattern. Something reacts with oxygen and end of story. So on Friday, we will pick it up from here. We'll also talk about balancing equations, and we'll get into a couple of other concepts there as well. Have a great day.